Welcome, folks. Thanks for being here. Those of you that are here in person, those of you that are here remote, thanks for being here. So, longtime members know the first question I always ask is, who is hiring? We have a smaller room today in person than we have virtual rooms, so not everyone can say it. If you're virtual, go to the job postings channel of nyhackr, our Slack. You can find that at nyhackr.org, or we'll put a link in YouTube to get to that. So if you're virtual, tell us you're hiring there. Does anyone in the room hiring? Anyone? Where's Noam Ross when we need him? He was always hiring. All right, so no one's hiring in here. No one's getting a job today from this meetup group unless someone posted virtually. Those of you that are here in this room, the pizza is from Lazzaro's. So everyone should go to bit.ly/pizza poll and vote on the pizza. Let us know how it is. So some of you are regulars. You know what to do. You go there, you can rank it on a 5-point scale, and this data is available. We provide it as a live feed for anyone to go to. It's actually at nyhackr.org as a live bar chart. This is rapid, high velocity data, but it's always being updated, and we can get you a live feed as JSON data if you want. So let us know how it is. Seriously. And folks that are virtual, if you got pizza, let us know where it's from. If you got something that's not pizza, I don't know why, but if you did, let us know where you got. So let us know either in the Slack. Again, that's nyhackr.slack.com. If you need a link for it, you go to nyhackr.org and let us know where you got it from. Or you can just tell us right in YouTube where you got your food from and let us know how you're enjoying yourselves. People in the room, there's a bunch of stickers in the back. The more stickers you take, the fewer I take home. Right? So enjoy the stickers. There's some new ones for you. You haven't been in a while. So enjoy the stickers, folks. All right. We have next month, we have R in Government. Is the conference R in Government conference about both R and other friends. It's R, Python, SQL, Julia, Go, whatever is open source in the government. We have some past speakers in the room right now. We have a future speaker. Where'd you go? Right there, we have a future speaker, and some of you aren't there. We have David Shore from Blue Rose Research. We have David Meza from NASA, Abigail Haddad from Capital Technology Group. We have Selene Stromgen from the FDA. We have Dusty Turner from the Army. It's going to be a really fun time. Lots of good talks. We're really excited. We'll be doing ticket giveaways to someone virtual and someone in the room. So if you're in the room, your name's been entered. If you're virtual and you signed up for the talk, you'll be entered. And after the talk, we will give away free tickets to the conference. For anyone who doesn't win a free ticket, if you just want to attend but you want a discount code, you can go to rstats.ai and use code nyhackr. That works for everybody in the room, and it works for people virtual. You get a 20% discount code using nyhackr. That's the code. All right. Then, let's see what else is on my announcement. So, some of you signed up for this talk about Taylor Swift. Some of you signed up for this talk since yesterday about mapping in R. So to all you Swifties, I'm sorry, our speaker canceled very, very last minute, but we're going to hope to reschedule this Taylor Swift talk within the next few months. Thankfully, our October speaker was able to come in and save us and move his talk up a whole month, giving him 1 day's notice. So folks, I hope the folks that want to see you can, and that a bunch of people didn't get excluded because they couldn't make it because it was 1 day's notice. But hey, sometimes we have to roll the punches. So everyone, a big round of applause for saving us, making this happen. Everyone, please welcome Art.
All right. Thank you very much for coming out tonight. And again, apologies if you were expecting some Taylor Swift stuff. Actually, this talk has been ready since August, so I was able to go at a moment's notice, but I haven't rehearsed the patter yet, so please bear with me. So we're talking about geospatial mapping in R tonight, and let me warn you in advance, this is so much fun and so easy to do, you will very quickly go down a rabbit hole like I did and just trying all sorts of crazy stuff. But hopefully when you leave here today, or when you click away, you'll learn about the huge strides that have been made in just the last couple of years in open source GIS, whether it's R or Python or anything else. The power that is just right there in your hands now is just truly amazing. And in R, making really cool maps and doing very powerful visualizations is super easy. And we'll demonstrate that by creating an animated flood inundation map to see how rising water levels cover landmass. So who am I? Well, first of all, I'm not a data scientist. I'm a retired investment executive. So my job was making bets on whether the Deutsche Mark would go up based using other people's money, or the euro. I go back that far before the euro. I do some consulting for Posit to try and make contacts for them in financial services. But I'm a data science hobbyist, a citizen data scientist, if you will. And you can see the other work I do on my blog, outsiderdata.net. So let's talk about GIS. In the old days, this is going back to the early noughts and 90s, GIS data was something civilians couldn't access, right? Governments were using this stuff. They had their data sets, but they were locked up. And they typically used proprietary software. The most popular one is ArcGIS by Esri. And it's a great package of tools, super powerful. And the data, which has become a geospatial data standard, is something called shapefiles. So those are still in use today. But what is different today is that you and I can access all of that stuff. So for instance, an example of a modern tool chain in the open source world is a package, nothing to do with R now, called QGIS. And I recommend all of you check that out. So Esri is still out there. And again, it's a terrific and very powerful tool, but it's a commercial tool, proprietary. So you could pay $765 a year for a personal license for ArcGIS, or you can just download the open source QGIS and do a tremendous amount of cool stuff with that on the fly. So for prototyping, for moving things from one side to another, before I start working with R, I often use QGIS. If you folks are familiar with drawing software or photo software, you know about GIMP, which is the open source version of Photoshop. So it's kind of like that. All right, so in R in particular, there's a number of packages you should be familiar with. And these are all, so fresh, really. It's just really been in the last 5 years that this stuff has become very widely available. So SF and the Terra packages are for manipulating spatial objects. Map tools and Leaflet are used for getting interactive maps, and we'll see that in a minute. Rayshader, and we'll see some examples of that in a minute, is for 3D rendering, not just maps, but all sorts of areas within R. And OSM data is a package that lets you go out to OpenStreetMaps and get map features. Elevator is a package that lets you get topography, so you can do topo maps, but also bathymetry, so you can get depths underwater. Now, you use these tools to access data sets. And again, used to be proprietary. You couldn't get them for any money. But nowadays, there's so much open source data out there, crowdsourced data. Some of the places that I get my data from is OpenStreetMap, and you may be familiar with that. There's also Open Topography for topo data. The U.S. Geological Service does a really nice job of making their data sets available very conveniently to either download or get programmatically through their API. But also, your regional or local government probably has a lot more publicly available data. I saw a tremendous talk at the Posit conference last week where the city of Chicago was very embarrassed because their property tax analytics were systematically overestimating the market value of low-value properties and underestimating the market value of high-value properties. And they used linear regression models in SPSS, and they moved that workflow over to a machine learning model based in R, and really rectified that problem. So 50,000 lines in proprietary commercial software, SPSS, was systematically making embarrassing mistakes. They moved the tool chain over to R. But why that's interesting for us in this talk is it's all available. They've made it all publicly available. You can get all of that data about Chicago properties that they're using to make their property tax assessments freely available online. So again, a lot of regional governments are doing a great job. You can probably get the property tax maps and so forth for your town online now as well. There's also LiDAR scans, so you can get 3D imaging that's programmatically usable for urban spaces, rural spaces, whatever. So you can get all the skyscrapers in New York, Chicago, wherever. You can download those as geospatial objects and use those in ours. So that it's just crazy how much stuff is out there. Finding it is sometimes tough. Getting exactly the right file that you want to download is kind of tough. Searching these public databases is kind of tough, but it's all out there. It's just really amazing. Now, some of them require, are still available at cost, for a cost. Most of them are free, but a lot of those require an API key. Census data would be an example, where you need a key. So this is just a quick aside. You may be tempted, if you save your code on GitHub or some repository, to type in the key as part of your script, your code. Don't do that, right? So the best practice these days is to save it in your R environment file and call it from there. And we're getting a thumbs up there. Thank you. So important stuff. Now, let's talk about today's topic. So this is going back a few months ago. You folks may remember that a dam near Kherson in Ukraine was blown up. We don't know who did it as of now, and it's tough to figure out. You can come up with reasons why both the Russians and the Ukrainians might have wanted to see that dam blown up. But it was a humanitarian disaster, because when dams break, as we saw in Libya last week as well, people downstream have a tough go of it. So this is just the water pouring through the breach in the dam, and everything downstream was inundated for the next few days. Eventually it drained out, of course, but not before a tremendous amount of damage had been done. So a real nasty thing. So what we're interested in doing is, can we model what happened using geospatial analysis, R, and can we do it in a visually compelling way? So the answer to that is yes, of course. So we'll start with magic trick number one. That is, can we visualize the affected area? And again, this shows, I call it a magic trick because you can see just how few lines of code we're doing to generate this. Not only that, but this is an interactive map. I can drive around here and we can look at the area, we can zoom in, but that's just a few lines of code. As you can see, all I have is I just had to describe the four corners in latitude and longitude of the area I'm interested in, and then put what the leaflet package calls tiles, layer them on top of each other. One is from Esri. Again, those are the guys that make the commercial ArcGIS software, but they have a lot of their stuff that's now freely available as well. So we've got the imagery data from Esri, and then from a data source called CartoDB, we have the labels to overlay on that. And so right off, in terms of our exploratory analysis, we can make a few observations. One is, you can see the dam is right about where my hand is waving right there, because you can see the swampy areas below, and there's the river delta of the Dnipro River. And if we zoom in a little bit, see, this is all interactive, real-time, incredible. So there's the dam running vertically down from just upstream of the dam. You see a canal, and that provides, I don't know if it's most, but a lot of the fresh water to Crimea, excuse me. So one reason why the Ukrainians might have wanted the dam to be gone is that it cuts off freshwater supplies, or reduces freshwater supplies to Crimea. You also see those crop circles there. You're probably familiar with these radial sprinklers. Those are all being fed from that reservoir upstream of the dam. So this is an agricultural disaster for the farms upstream of the dam. And these swampy areas down below, you can see where there's no human features there, are all presumably going to be underwater. Now, how much gets underwater is what we'll soon see. Now, let me introduce the simple features. So this, again, we were just doing exploratory data analysis there. So now let's start doing the real work here. We're going to create a spatial object for all further manipulations. This whole project we're doing here is essentially building a stack. We're doing layers, both visually and programmatically, that have more and more information. So we start out with just a bounding box, as it's called, which is the rectangle that we're interested in latitude and longitude. And we're going to turn that into a simple features object, which is a type of spatial object. And it's noteworthy because it includes the map features and includes metadata about the map or the spatial region that we're interested in. And this case right here, we've just created an empty shell. It has essentially just the only features it has are the corners, the bounding box, and it has something called the CRS, geodetic CRS, which is the coordinate reference system, and that's going to be important here later on. Now, the cool thing for nerds like me is that a simple features object is just really a data frame with metadata. That means you can manipulate it just like you do a data frame using your normal workflow in terms of adding columns, mutating columns if you use dplyr type stuff. So in this example, I just add a couple more data points to this spatial object. A vector of strings called corner 1, corner 2, right? This is useless and not particularly interesting, but it shows how you can use regular R workflow to manipulate these simple features objects. You can also extract the simple features points using your conventional ways of indexing into data frames. So a lot of familiar ground already there with those spatial objects. So that was a simple features object that contains the data about our geographic object. Now let's introduce another type of geospatial object in R called a raster, and that's not just proprietary to R, that's in a lot of things. But this is just a matrix with a value for each point or pixel, if you will, on the map. Now, that value can be anything we want, but for our work today, we're going to get our raster with each pixel is represented as a number that represents the elevation above sea level of each point on the map. So remember, a simple features object is a description of the map, while a raster object is a drawing of the map. But both of these things are geospatial objects in R that have the same kind of metadata. So again, you can manipulate that matrix using the same kind of any tools that you use to work on matrices in R, any techniques you can use on the elevation matrix, but again, it preserves the metadata. So in this case, we've taken the bounding box that we already established and used a different package called elevator, which gets elevation data to retrieve that elevation data. Now you have to play around a little bit with the resolution of the thing, and how much data you get, and it's a lot of trial and error. But in this case, we've retrieved a matrix that, as you can see by the dimensions, is 1980 by 4560, and the range, the values there at the bottom, are minus 51, so underwater, by 51 meters, to a high of 107 meters above sea level. So that's the range. And again, you see that CRS there as well. And the extent is, again, just those four corners that we were already familiar with. And it shows, the resolution shows you the dimensions of each pixel. So all of that stuff is pretty English readable or legible. So that's pretty good. And again, it's just a matrix that you can manipulate regularly. So again, since that's just a matrix, we can do a quick and dirty plot to see what that looks like. So we just set a palette color ramp from blue to green. We're not doing any special mapping software or packages to do this. We're just doing the basic R plot of a matrix with a color scale that is intuitively understandable to us. And you can see the latitude and longitude on the axes, and there's that river delta, just expressed as colors is the elevation. Super easy. Now there's no elevation data in that, so we're going to introduce a new package called RayShader. And this, I'm going to digress for a second about that, because this thing is the shizzle. It's a person by the name of Tyler Morgan Wall dropped this like a bomb onto the R world, I don't know, about 5 years ago maybe. And it basically does 3D ray tracing on R objects. And you can use that on regular ggplot objects, or you can use that on these geospatial objects like I've done there on the left, showing topographic map and the sun rising and falling over that mountain lake with a different topo map for each day as we go through. So just really fun stuff. And this is where you can go down the rabbit hole, because it takes a long time to get all this stuff right and then animate all of that stuff, but it's terrifically fun. Other people are doing just beautiful works of art with RayShader. So here's just some more examples of the kind of graphics people are doing with RayShader, and they're just gorgeous, just really nice stuff. So super powerful. You could spend the rest of your life figuring out all the things you can do on that. And Tyler isn't resting on his laurels. He keeps dropping new versions with new features every couple of months on this thing. It's pretty incredible. Now, we're not going to use any of this cool stuff, actually. We're going to use one particular feature of RayShader, which is its ability to detect water based on adjacent pixels in the raster that have the same elevation. If there's a big enough flat area where the elevation elements in the matrix are the same, we can tell RayShader to say that's water. So here's an example of again, we're just taking the raster, turning it into a plain old matrix, and then we're using some RayShader code to add water and detect water and add that as an overlay to a base map. So, and then we plot that. So that is the RayShader object we've now created, where that shading is based on the ray tracing that RayShader is doing. And not surprisingly, the blue is everywhere RayShader has detected enough pixels of the same elevation to call it water. All right. Now this then is the key that unlocks this ability to create the inundation maps, because it's detecting water where everything is the same. But what if we arbitrarily start changing pixels to be the same as the pixels around them? And RayShader will falsely detect that as water, although, again, for the purposes of flooding, maybe it's not falsely. So let's build our complete image now. So add overlay lets us add to our base maps. So we're going to add a satellite view as our first layer on this thing. And here again, if you look here, you can see that we're getting that world imagery from the Esri service like we did at the beginning of the talk, right? So this is, you've already seen this image. So this is now, but we're just using RayShader's functions to create this map. But that's all we got here. We've just got the base image as the first layer of the object. Now, what do we want to do next? We're interested in showing human presence on here. So you can't really see it at this resolution. You can, of course, see the grids for the fields, but it's a little tough to see exactly where the human presence is. So one way to do that is to get roads and overlay them on there. Now, we're going to get the roads from OpenStreetMaps, and we're going to use the OSM data, OpenStreetMap package, to get that. So we go ahead and retrieve, here's the code to retrieve the road data from OpenStreetMaps. And at the end of the talk, the GitHub source will be here, so you can, if you want to dig into the particulars of that. But notice, the thing to notice here is, what does it return? Aha, you've already seen this. It's another simple features object, which the geometry in this isn't points like we did when we created our empty thing. It's lines, line strings. And the geometry is just individual vertices of the lines to represent the roads. And you see the bounding box, you see the CRS there, the coordinate reference system. And you see the other features in addition to the geometry. So the actual location of the roads is contained in that geometry column of the data frame, but there's also the name of the road as one of the features in there. And then a unique identifier is just the ID. So again, it's a data frame that you can manipulate very easy. Now, let's go ahead and point out one particular gotcha. I shouldn't say it's a big gotcha because it's so easily fixed. But all of these simple, you're going to be going out to different data sources, right? So you're going to be pulling roads from here, you're going to be pulling water from here, you're going to be pulling elevation from here, buildings from here, whatever it is. You may be using, 2, 3, or 4 different data sources when you start building these layered maps. What you have to make sure is that they're all using the same coordinate reference system. Now, everybody here knows that there's multiple ways of projecting a curved planet onto a flat surface. So if you look at a Robinson-Humphrey projection, it looks very different than a Mercator projection. And we don't know, or we can't guarantee that all of our downloaded data is going to have the same coordinate reference system. There's hundreds. And there's some that try to fit the whole Earth, because we know the Earth isn't perfectly spherical. Those are not entirely perfect. But then there's regional coordinate reference systems. Just for the Northeast United States, there's a particular CRS you could use. So like if you're downloading city data from New York City, you're going to see that regional coordinate reference system. We need a way of making them all the same. So there are functions in all of these packages to reproject one coordinate reference system onto another. So that's what we have to do. This is what this coordinate reference system string looks like inside our one of our simple features file. So it's a lot of information there. The only thing, like I said, you just need to make sure you understand how to use these transformation or reprojection functions to make them all the same. And you can extract, if you want to make sure A uses the same CRS as B, you can extract the CRS from B very easily and tell this to transform A into B. So a lot of stuff there, but simple to address. You just have to be aware of that. Now, remember we said a simple features object is just a data frame. So it turns out ggplot2, which most of you are familiar with, has a geom for simple features objects. So it understands, you can just feed it the simple features object, and ggplot understands it. So let's do a mapping of those rows that we just downloaded, which again, we saw it had the geometry, which were lines, and the names and unique IDs. So in this case, we'll use traditional ggplot workflow to plot the line file, line object, and for each of the different lines, we'll say color it according to the OpenStreetMap's ID, which there's a lot of roads, so we're going to see a lot of colors there. We're not really that interested in that. But that is using the geom, the simple features geom for ggplot, just plotting that road data. So you can explore and see what you got. And it's pretty easy to see where the river delta downstream of the dam is by where the roads are not. So that's going to be very useful for us to understand where the flooded areas have human habitation because of the roads there. So now let's generate the road overlay, and you'll use that road file, road object, to create another overlay for RayShader, because again, we're building layer on layer on layer. We're going to build a line overlay, use the generate line overlay function in RayShader, and turn that into an overlay that we can add to our map. So again, we're using a specific function there, generate line overlay. Now, so let's put our first two layers, our base map and our roads, together. And you can see there all that black area, those black lines, spidery lines in this plot show us where the roads are now. Okay, now here's where the cool stuff really happens. So we talked about this a little bit already. You can set any height in the elevation matrix below the water layer, below that we want to say is below water level, to 0. So RayShader will consider it water. So we could just use typical matrix operations to set any value below X to 0, and then RayShader will think it's water. Now the order of the overlay matters, right? Because any subsequent overlay will completely cover up any overlay beneath it. So we're going to we want to make sure the roads are displayed after the water, so we see them on top of the water, even though they're, of course, underwater. So here's an example of now what we're doing. What we've done is in this example, there's the first one where the water, we haven't done anything to the elevation matrix. So that's what is typically water. And in the one below, we've just arbitrarily said, if the elevation is less than or equal to 5 meters, set it to 0. And then RayShader thinks it's water. So now we can see what 5 meters of flooding looks like. Super easy, super cool. Now, at this point, I want to raise some caveats, because this is a dramatization, all right? I wouldn't submit this. This would be fake news if I said this is what the flooding was, right? We're simulating it. We're modeling it. And there's caveats there. We don't know exactly how the water affected each area at what time. Presumably when the dam broke, the areas closest to the dam got flooded first, and the areas farther downstream flooded last, and maybe less. We don't know what the peak inundation level was for each area. And now, of course, the water has receded. So again, while I think this does give an accurate idea of how tragic this thing was, we can't say this is exactly what happened. So now what we've done already is cool enough, I think, because we were able to animate this stuff. But now we're going to get even cooler, and we're going to plot the rising water level as an animation. So again, you don't have to go through this code line by line. It's all online. But basically, we're going to do these plots that you already saw, but we're going to loop through different water levels and save them as individual frames, individual images on our hard drive. So we're saving we're looping through the rising water levels and saving each one as a frame. And then I'm gonna overlay an annotated scale. I didn't want to bog you down in too dense code here. It was just me playing around. So again, you can see that if you want. But this is the code that actually puts the frames together as a GIF file. I don't know whether you folks like to call it GIF or GIF. I call it GIF. But anyway, so what you have, though, is just look at the different steps on this. It's very straightforward. Is first we resize each frame to be more manageable, a little smaller. Then we morph it so that it has so it kind of morphs from one frame into another, so it's less jerky when it flips to the next frame. Then we say image animate and then image write. So this is all using the Magic package, which is a super powerful image manipulator. But again, it's all programmatic stuff, and it uses the code from FFmpeg package. So, but Magic, if you work with that, you can find it's incredibly powerful. All right. So, ta-da! Here's the finished product. So, see that green legend on the side it was the little decoration I did. Again, I spent so much time just trying to get that little inset there, and it doesn't add all that much. But again, you can see this is a very compelling and dramatic way of seeing how those floodwaters are rising up. And you can see those road areas where there's human habitation that got underwater. And like I said, it was a dramatization, but we do know that there were lots of populated areas there that got flooded when that dam broke. So the south side of the river was generally the swampiest. That big dense area kind of in the upper half on the middle, that's the city of Kherson, which is fortunately a little higher elevation. So again, terrifically powerful stuff. And again, it's very simple and understandable once you start working with it, because you're doing it step by step, layer by layer. And you can see, for me, I was able to see gratifying results with very little code right away. And then, of course, you can add more and more and more as you go. So that's essentially it. And one of the things, FEMA redrew the flood inundation maps for New York City. So now my house is in a flood zone when it wasn't before. So I'm interested in trying out this project on Manhattan next. So, okay, so thank you so much for listening. This is how you can get in touch with me. I'm on my blog is outsiderdata.net. You can see the code on GitHub. And I love GitHub, and it's just for me because I have a laptop, I've got a desktop, I've got a weekend house, and I can share all my code and work on that stuff wherever I am. But also, all of my work is public, and it's ugly, right? Because it's just for me. I'm not writing for you. I'm writing for me. But on my GitHub, you can see just everything I do in R. But I'm a big believer in getting stuff out there. Dave Robinson said something that really stuck with me, and it caused me to start blogging. He said, "Look, don't be embarrassed about what you don't know, and that you're not a professional data scientist, because the value of the code that's on your computer is zero. So as soon as you put it out into the world for other people to share and see, its value increases infinitely more, right?" This is my social media stuff, Ada Babbage on Twitter and Mastodon, my homepage, artsteinmetz.com, and on LinkedIn, A. Steinmetz. So there you go.
Thank you.
Thanks a lot for coming. Thank you, folks, for online.
So let me start this off with a virtual question, then I'll ask some questions in the room. Do you know where, come here, you're not done. You're answering questions. Do you know where the elevator package gets its data from for the elevations?
Yes. Open elevation. Hold on. Let me go back to all the packages. Blah, blah, blah.
It was like way in the beginning.
Way in the beginning. Way. Open topography.
Okay. And that's good worldwide data?
I haven't tried everything in the wide world, but so far so good. It does Ukraine okay, and it does everywhere in the United States. But for when I'm doing United States topo work, like this like this ratiator thing. On the left, I used USGS topo data. So you can download historical topographic maps from USGS that are geospatial raster files. So they have the pixels that you see here and the elevation data as a layer.
Nice. Then I guess a follow-up question to the elevator data is, you passed it an SF object, and it took the bounding box from that and just returned a raster based on the bounding box?
Yeah, so you just use, you can feed, when the function asks for a bounding box, and you have to check this, of course, but a lot of the functions will are actually looking for a so-called extent object, which is one of the pieces of the metadata in a simple features file. So a lot of them, when they're asking for the extent, or the bounding box, you can feed it the whole simple features variable, and it will extract the extent from it.
That's nice. Cool. Do we have questions in the room?
I have a question.
Yeah.
Can all sorts of coordination reference systems be translated or transmuted into each other?
Yes, they can. As well, I'm saying yes because there's a standard. They're pretty standardized. Yeah. So you may run into one that is very custom or proprietary, but it's unlikely.
Can I comment on that one? So you can, but if you're using a raster image, and it's something very north in the U.S., and using something more near the equator, then some of the bend of the Earth starts to become a problem. So if you're using raster data, it gets a little messy mathematically sometimes if you move too far north or south.
Yeah, near the poles, it can get messy, right?
Sorry?
Near the poles, north and south poles, things can get messy. Yes?
Can you please go back to the slide where you discussed saving the frames?
Yeah, sure.
Okay, do you have any guidance on about how many frames we would want to do, or was that more of a automagic value?
How many frames we would want to do?
Yeah.
Any guidance? Well, because we know we're animating rising water by meter. So how many meters are we interested in? However many it took to create a really flooded area. So again, just in the interest of truth, I don't know what the maximum height of the water level was after the dam broke, but I know that the bottom of the dam is about 8 meters above sea level just experimentally. So that's why I saved 8 frames. And then I morph between it so there's a smooth transition. So you'll just have to experiment. I could do more frames, but it wouldn't show you anything because I'm going in integer steps, meter by meter by meter.
Thank you.
So basically I said so I took my elevation matrix and looped through that 8 times, and said, if the water level is, at or below the water level I'm interested in, set it to, actually I had to go to -2, not 0, to get what the -2 just happened to be what the completely unflooded river delta looked like.
And that's all ratiator, right? The code you're showing right now, that's ratiator.
That's ratiator, right. That base map is the base map, and then add overlay, add water, add overlay those 3 things are ratiator functions. And then save PNG is not. That's from the PNG package.
And ray render is how you can make like the 3D fly-throughs, and that's different than ratiator. It's like related but different.
Yeah, ratiator calls a lot of ray render functions, so it just wraps it up it's in some sense a wrapper for ray render that makes it more easy to work with map data, spatial data, and like ggplot code, things like that. But yeah, ray render, when I do cute little flyover stuff, there I use ray render.
Okay. And could you make sure you repeat the question when he asks?
Yeah.
About once a year, I'll find myself wanting to make a map, and I'm not like a big front-end dev, and I want to share it with somebody who's not my network or who's not a nerd, and so like you can do like Leaflet and Shiny, but that doesn't really scale well or on your blog very well. Do you know any tools that can produce code that can go like be JavaScript or just kind of be a publicly accessible thing?
Well, yeah. So these rendering tools that I'm using, again, I'm saving to PNG files, right? So save PNG as you see here. So obviously, once you save it as a static image, and all of these packages let you easily do that. You've got
rather like more interactive things.
And so on more interactive, well, then you're still in the world of HTML. And in this case, I'm using R Markdown, or its successor, in particular, Quarto, to generate a web page that has all that interactivity. So you have to have HTML widgets if you're going to have interactivity. Now, you may be comfortable with JavaScript. I don't know JavaScript from a hole in the ground, but I do know R Markdown and Quarto. So if I save those files, those create the HTML widgets, and you can save those files. And it's like I said, it's converted to HTML with I assume some JavaScript elements in it. But that's all invisible to me, and I don't care. So.
Thank you.
By the way, I've been having a huge amount of fun with Quarto, which is the new publishing framework from Posit that works with anything: JavaScript, Python, R, and it's just super easy. This is a Reveal.js HTML. This Reveal.js is what is underneath all this HTML in here, and I don't know anything about that. I just said, set format to Reveal.js, and voila, we have a cool slideshow. And I don't know how it works. It's just magic. Other questions? Yeah, all the way in the back, then we'll go to the next.
So first of all, really great talk. You mentioned kind of like alternatives to this, like ArcGIS and QGIS. I don't know how much you've worked with those, or things like GeoPandas and Python.
Mm-hmm.
Do you have any high-level thoughts on just what R in particular make easier compared to other alternatives, and what R could do that those couldn't do?
I'm sorry, what is that?
Repeat the question.
Oh, yes, I am going to repeat the question. So any thoughts on what R in particular does in the geospatial realm versus, say, Python, which has GeoPandas? Well,
or QGIS also.
Or what's that?
Or QGIS.
Thank you. Boy, it's getting late in the day. QGIS. Well, QGIS is very much an interactive tool for loading, manipulating, and then saving GIS workflows. Very powerful, but it's not, while it does have, I think, a Python interface that you could go in and do little Python scripts that do stuff in QGIS, it's not strictly programmatic. It's more like Excel or something like that, where you might do VBA in it, but you manipulate things on the fly and then save your projects. On Python, okay, I'm not well versed in Python. I assume GeoPandas is basically a full-featured package. I don't think there's a whole lot of you can't say, oh, R is better for this and Python is better for that on anything anymore, because pretty much the day somebody releases a Python package that gets huge uptake, there's an R version of it. Keras, Torch, Scikit, all of that stuff, all is just as usable in the R world. So I think whatever vernacular you're most comfortable with is where you're going to get the most work done. The only exception to that would be RayShader. I don't think there's a Python analog to that at all, and that's just tons of fun. But otherwise, I wouldn't. I'm sure the geospatial tools in Python are essentially the same thing, and just as convenient. Like again, discovering simple features was a miracle to me, because again, it just makes everything is so human readable and easy to manipulate. And I'm sure GeoPandas is the same thing. Yes. You.
So that was a great talk. And could you validate your model? For example, can you get the actual satellite image of the flooding and see your model?
Yeah, the short answer is yes. I haven't tried that. But if you Google around online, you can see satellite images of the flooding. I mean, it's crazy the way this war is being covered by satellite imagery, right? So you know, something gets blown up today, and 2 days later, you see the satellite imagery of the destruction on Telegram or wherever. So you could get any one of those. I haven't done it, but you could look for those images, and then using QGIS, this is what I use QGIS for all the time, georeference those images. So you basically, there's a so-called georeferencer tool in QGIS that lets you click on a picture, on a point on your, let's say, JPEG image, and then click on a point on the OpenStreetMap image and map that point to the image, and you do that 10, 20 times or whatever, and then that will twist and transform that JPEG image so that it overlays perfectly on the map, and then you can save that as a geospatial raster, and you could overlay that on your R imagery very simply. So, but again, the georeferencing feature of QGIS is what I use it for all the time.
I have another question is that you use the different sources, you know, some street map or other QGIS. I think the map data are collected at different times. So can you, so for example, some street data is collected in the 2019, and you use the geographic elevate data is collected in 2020. Can you align the time axis of the data?
Yeah, you could. I mean, that would be a manual process. But so, for instance, I mean, this isn't what you're. So the question is, can you download different data from different time frames and step through that time, through time? Is that what you're asking?
So in the talk you're not saying about the time. So my question is, if you can align the time axis as well, not just the geographical. So you are saying that you can do some projection or other.
Oh well, yeah. I mean, again, I hope I'm understanding what you're saying properly, but that is one of the things that I would say simple features is really, really well suited for, because we have however many rows of geospatial data, and each one of those rows has some features, like in what we saw earlier was the name of the street and the line that represented it. There's nothing stopping you from saying, if you've got multiple road files, because roads change over multiple years, you could add time as another column in your simple features data set, and filter, again, using your usual data frame manipulation tools, filter by year and create a frame, save it as an animation frame each year. So it's super easy to do if you already are comfortable manipulating and adding columns and filtering data frames.
Thank you.
Anything else?
Another virtual one.
Yes.
I'm not mic'd right now, so you might need to repeat this. There's recently came out like the Overture maps.
Overture maps.
Yeah, it's a coalition of like Microsoft, Facebook, and Amazon to compete against Google, and they seem to be releasing like a lot of similar data to OpenStreetMap. Mm-hmm. So I was wondering if you knew about them, if you had compare them. I guess you haven't yet.
Do I know about the Overture project? No, this is the first time hearing of it.
Okay.
Yeah. But there's a lot of different data sources besides OpenStreetMaps for mapping data, not just OpenStreetMaps. And it's they have a lot more things than roads on OpenStreetMaps. So they've got locations of businesses. I've seen some code examples where you can, with just a few lines of code, say something like Google Maps does very easily, but you do it programmatically, say, show me all the hamburger restaurants in a 5-mile radius of this particular point. So OpenStreetMaps can do stuff like that. But again, I haven't looked at Overture at all.
So I haven't used Overture specifically, but I have used some of the early Facebook data from when they bought Mapillary, and it was pretty good. We used it for fire hydrants for insurance purposes.
Would there be any reason to use that over?
So he was just saying, I'm repeating it. So you were saying Overture was good for finding fire hydrants for insurance purposes.
Well, so it was Mapillary. Facebook purchased Mapillary in 2020, and
Yes.
the Mapillary data, which is probably going into Overture.
Oh, so the Mapillary data is probably going into Overture. Yeah.
And we used it because it was another free data source. Like they released it for free.
Well, free stuff is good.
Yep.
Yeah.
I used Overture recently for a personal project and can confirm it was very easy and the data was quite good.
Okay, one endorsement for Overture.
1.5.
1.5.
Yeah.
Okay. So I'll look at that. Thank you.
Anybody else have any questions? And I'll check online to see if there's any more online, but anyone else have anything here? Okay. Then I guess a big round of applause for our last
Thanks a lot.
speaker.
A lot of fun.
Good, I'm glad.
Appreciate the invite.
It came through. We'll have to get you to give another talk again soon. We'll give you more notice. Yes. Thank you everyone who attended virtually. Thank you everyone who attended in person. Those in person, if you'd like to go to the bar, we'll probably go to the bar. It's usually just, what's that? The Beer Authority right across the street, unless anyone knows a better bar. I'm taking suggestions. If you want to go, come with us. Those of you virtually can't come with us, unfortunately, but we'll see you another time. Remember, we have the R in Government Conference next month, October 19th through 20th. Go to rstats.ai/gov to find out more. Don't be late. He's one of our speakers, as I'm pointing at him. And also, next month meetup, October 10th at NYU. That's everything. Take home the pizza, people here, because we have a lot of it. And see you at the bar, and see you next month.
The technology worked. My wife was watching the live stream from Anguilla.
Holy crap, that's awesome. Yeah. Nice. I should pay attention to everything you said.
Yes, I'm sure.
Nice. Nice. Well, thank you, everyone. See you next time.